In our previous video, we looked at these numbers 1, 4, 9, 16, 25, 36, and continuing on, numbers like 49, 64, 81, 100, 121, 144. These are all what we call perfect squares. And again, they're perfect because when we take their square roots, they turn out to be whole numbers. So if I take the square root of 1, I get 1. The square root of 4, I get 2. The square root of 9, I get 3, and so on and so forth. 4 all the way down till I get to the square root of 144 equal to 12. So we're going to use this concept of perfect squares and the fact that square roots and squaring cancel each other to simplify square roots. So for instance, if I were to take the square root of 75, now I could break 75 down into a product. I can break that down into 75 times 1. I could break that down into 25 times 3. Now, both of these are have perfect squares in them, but I'm looking at the one that is other than 1, and I'm looking at 25 and 3, because what I can do at this point then is to break this into two square roots. So I have the square root of 25 times the square root of 3, and then we know from our past experience that the square root of 25 is 5. So our answer is 5 square root of 3. Now I can't break 3 down into any further perfect square factors. Therefore, this is what we call a simplified square root. Or more generally, a simplified radical. Okay? Taking another example, if I took the square root of 72 now, I can think of different ways to factor 72. Now, I'm going to show you a thing called, I guess the best way to describe it is you are basically prime factoring the number. So if I look at 72, and I want to restate that as a bunch of multiplications, here's how you go about doing that. I'm going to take the prime numbers. Now, prime numbers are numbers that can only be divided by themselves in 1. The smallest prime number is 2. The next prime number is 3. 4 is not prime because it can be divided by 2 as well as itself in 1. So the next prime number is 5. 6 can be divided by 3, 2, 1 in itself, so it's not prime, but 7 is. 8 and 9 aren't prime. 10 isn't prime, but 11 is. 12 is not prime, but 13 is. 14, 15, and 16 can all be divided by other numbers other than itself in 1, but 17 is prime. So is 19. So is 23. So I'm going to take 72, and I want to find out what multiplication combinations could I have that include only prime number factorizations. So I look at the smallest prime number that will fit into 72 evenly, and it's 2. So if I go 2 divided by 72, I get 36. Well, gee, 36 is still even, so I'm going to divide that by 2. So let's see, 36 divided by 2 is 18, and 18 divided by 2 is 9. Well, 2 doesn't fit into 9, but the next prime number up, 3, does. So 9 divided by 3 gives me 3. So 72 is equal to 2 times 2 times 2 times 3 times 3. All right? So if I take 72 now and I could rewrite this again. So I'm looking at a perfect square. Here's 4. Here's a perfect square of 9. So I can rewrite 72 as 4 times 9 times 2. Well, guess what, guys? The square root of 72 is equal to the square root of 4 times 9 times 2. Well, I can break this down into 3 square roots. Square root of 4 times the square root of 9 times the square root of 2. The square root of 4 is 2. The square root of 9 is 3. And I'm left with the square root of 2 inside this. So the 2 is left inside the radical. 2 times 3 is 6. So I have 6 square root of 2. So this is simplifying a radical using what we call the ladder method of prime factorization. Ladder method of prime factorization. Okay, we'll give further examples here, but again, the other way to look at this is try and look at, gee, is there a way of finding the biggest perfect square factor of 72? Well, if I recognize that 36 is a perfect square, I could also look at 72 as 72 is equal to 36 times 2. So if I take the square root of 72, that's the same as the square root of 36 times 2, which is the square root of 36 times the square root of 2. Well, the square root of 36 is 6. So I'm left with 6 square root of 2, which is exactly as I got down here. So there's basically 2 methods you could use for simplifying square roots.